Hey everybody, today we're going to be discussing linearity. It's going to be a short discussion. I'm going to mathematically define linearity, and then I'm going to explain its physical implications and what it means for the theory of physics. So, linearity is very simply explained as just the ability to combine solutions in physics. Um, and what that means might not be so clear right now, but hopefully by the end of this video it'll make a little more sense. As far as mathematically how it's defined, the first thing you have to know is that most physics theories, in fact, I believe all theories of physics and in math, can be described this way, or it can be, I guess, sort of boiled down to that. And what this is we have an operator A acting on an unknown, and in this case I'm just going to say one unknown, but this could be a vector, could be many unknowns. One unknown equals 0. And this can be non-homogeneous as well, and that could equal like a constant, but we're going to say 0. This is about the simplest case you could possibly have. So what's an example of this? Probably one of the more famous examples of this is the simple harmonic motion differential equation, which would be the one that Newton found that described why springs go back and forth. So we'll just derive that real quick. F equals ma, but a we know is the second derivative of x with respect to time, right? We also know that for a spring, force is dependent on the position of the mass that's being oscillated, minus kx. So we'll equate those, m d squared dt squared, and I'm going to put the x, so this is kind of like d squared dt squared, or the second derivative acting on x. You can kind of think of this as an operator itself. And coincidentally, that's a linear operator, but anyway. So we'll group it up here, and we'll see that m and then d squared dt squared plus k, and then I'm going to put these parentheses here, and you'll see why in a second, and that's kind of a bad k, acting on x equals 0. But look at this and look at this. What is this here? This whole thing is just my operator A, right? And then this is my unknown u, and that's equaling 0 here. So that's an example of a physical theory, the theory of simple harmonic motion, that could be described as an operator acting on an unknown equaling 0 in the homogeneous case. So, just kind of a proof that this is true. But linearity is specifically a set of properties for that operator. And in the case that I just showed you, that actually was, that whole thing was a linear operator. So I could show you on that example, but those properties for A, the first one is that A acting on, and we'll say B, U, where B is a constant. B is a constant, just a scalar, multiple, and U is still my unknown, equals B times A acting on U. Abu equals bow. A acting on B times U is equivalent to just the scalar multiple times A acting on U. You can pull scalars out. That's pretty much what it means. Scalars don't really matter to a linear operator. 2, you might call this the distributive property, I don't know. But if I have, like, let's say I have 2 unknowns, U1, U2, that can be represented as A acting on U1 plus A acting on U2. So A acting on the combination of 2 unknowns can just be represented as A acting on the first unknown plus A acting on the second unknown. This leads to a third property, which is really the one that I want to hammer home. So I'm going to circle it and be like, oh, this is the big one. A acting on, and we'll say, I'm going to define two constants, little a and little b, right? A, u1, plus b, u2. Okay, so we have A acting on you can call this a linear combination of A times u1 plus B times u2. Okay, so we just have two, what we call in physics solutions, this u1 and this u2, and a combination of those solutions in our theory. This whole thing is acting as our unknown. So A acting on that will be A, and I'm actually going to need more space for this, I think, but that's okay. Will be A, little a, sorry, times A acting on u1, and then B, A acting on u2. Okay? You can see that? Yeah. So we pull the constants out. That's because of this property. And then we know that distributing the A across we can do as well. So everything's legal. That ends up that way. But we look at this, and A, like, for example, if I just come up here and say, like, A times this is A times this. Well, what's A times 0? 0. So any scalar multiple of my thing is still equal to 0. So this thing is equal to 0. But also, this thing is equal to 0. So this whole thing equals 0. What that's saying is a combination of valid solutions, meaning like if I just took this and I just took this, those are solutions, I'm happy. I combine them and I say I'm taking both of my solutions that are independent solutions, but I'm going to consider them together, is another solution, is a third solution. So what does that mean in physics? I mean, that's all good, and mathematically speaking, it's fun and it's easy to prove. You know, if by the way, if anybody asks you to prove linearity, you just have to prove these properties. I mean, it's not that hard. You just make sure that if you multiply by a scalar, it doesn't change anything, or you can pull it out, and then see if it distributes. But in physics, what does that mean? Well, for example, we'll take the theory of electromagnetism. Let's say you want to call your friend in China. So you're sending electromagnetic waves his way, and he's over here in China. But your mom is down here, and she's a beautiful woman, so she has hair. Okay? And she wants to call her friend in the North Pole. Maybe your dad. I don't know. Well, guess what? This wave and this wave are both independently solutions to Maxwell's theory of electromagnetism. So we'll say this wave is solution 1, and this wave is solution 2. So this wave, solution 1, this wave, solution 2. But all of it together, solution 1 and solution 2, unless electromagnetism is a linear theory in experiment, when those things cross and they meet each other, and all of a sudden they're combined, it better be a new solution. Because otherwise what would happen is, when I have my two waves together, the universe is like, well, there's no guarantee in general that that's going to be a solution. I knew that this thing was a solution, I knew that this wave was a solution, but the combination of the two may not be a solution. Now, luckily in our universe, what happens is constructive and destructive interference, but because of the different velocities, different directions of the velocities, and when they cross, after they cross each other, they don't care about each other anymore, and your mom's call gets to your dad, and you get to your friend in China. Without linearity, that wouldn't happen. We couldn't have radio, and we couldn't have internet, and we couldn't have anything. Any Wi-Fi, anything like that, because all of the waves from all those things talking to each other through the space around us, the combination of those waves together wouldn't be a solution. And when they cross, the universe, I guess something magnificent would happen. But we don't know, because in our universe, it's fine. It's called the superposition principle. But anyway, that was a short discussion of linearity. Hopefully you learned something. Yeah, thanks for watching.